Consider the function f of x is equal to 7 tangent inverse of x to the sixth. Differentiate the Taylor series about 0 for f of x, identify the function represented by the differentiated series, and give the interval of convergence of the power series for the derivative. Okay, so you probably have the Taylor series expansion for tangent inverse of x written down somewhere. Okay, I'm going to derive that really quickly, and then we'll move forward with this problem. So how am I going to derive that? I'm going to start with tangent inverse of x, and I'm going to take the derivative of that, so d over dx. Okay, so the derivative of that is 1 over 1 plus x squared, correct? So I'm going to rewrite this as 1 over 1 minus a negative x squared. Same thing, correct? Okay, now why would I write it that way? Well, the reason being is that I know for a geometric series, if it's of the form 1 over 1 minus r, then that can be expanded as 1 plus r squared plus r cubed plus dot dot dot, right? Okay, so in our particular case over here, our r is negative x squared. So if r is equal to negative x squared, then I can expand this into, so let me rewrite this. I can expand this into here to here to here, and now I expand it into 1 plus r, right? Where r is negative x squared, plus r squared, or negative x squared squared, plus r cubed, or negative x squared cubed, plus, and we could keep going, okay? Which means that we have the derivative of tangent inverse of is equal to 1 minus x squared plus x to the fourth minus x to the sixth plus dot 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 dot, right? Okay, so did that help us expand the tangent inverse function using Taylor series or using geometric series? Not yet, but we can do this. We can integrate both sides of this little equation here, and we can integrate this other side term by term. Okay, now if you integrate, but it's already has the derivative, we're just going to say, okay, well that side is inverse tangent of x. And if we integrate the right side term by term, that gives us x minus x cubed over 3 plus x to the 5 over 5 minus x to the 7 over 7, and so on and so forth, right? Okay, so we now have our Taylor series expansion for tangent inverse using geometric series. Okay, so the problem says that it wants us to differentiate the Taylor series about 0. So here's the Taylor series about 0. So all we have to do is take the derivative of this thing, but we also have to first, remember we weren't dealing with the exact function. We have this 7 and this x to the 6th power. So let's first say, okay, well if this is tangent inverse, then let's multiply that by 7. And let's substitute the inside with an x to the 6th. Okay, so with that substitution, we get 7 times x, but instead we're going to substitute an x to the 6th, so x to the 6th, minus 7 times, it says x to the 3rd, but we're substituting an x to the 6th, so x to the 6th to the 3rd. So if I substitute this in here and raise it to the 3rd power, that is the 18th power over 3. Plus 7x to the 5th, but I'm subbing in an x to the 6th, so that's 5 times 6 is 30 over 5. Okay, and then our last term that we've written out here, we would substitute an x to the 6th here, and it would get raised to 7 power, so that's x to the 42. So 7x to the 42 over 7, and we could keep going. Okay, now it wants us to take the derivative. So this is the Taylor series expansion for 7 tangent inverse x to the 6th. But now we need to take the derivative of this thing. Okay, so if we take the derivative, so d of 7 tangent inverse of x to the 6th dx is equal to 6 times 7 x to the 5th minus 18 times 7, x to the 17 over 3, plus 30 times 7, x to the 29 over 5, and then minus, let's see, this one would end up, the 7's would cancel, so that would make that a little easier. So that would make that minus 42x to the 41, and then of course that would keep going. Okay, so that's the derivative term by term. Okay, now we can clean that up a little bit. If we clean that up a little bit, that becomes 42x to the 5th minus 42x to the 17 plus 42x to the 29 minus 42x to the 41. I think you see the pattern here, right? Every term has a 42. They are oscillating from positive to negative, which is going to come in handy knowing that soon. And then they are going up by a power of 12 each time. Okay, so that is the answer to A, where it says differentiate the Taylor series about 0 for f of x. Okay, so that's your answer for A. Okay, for part B of this problem, we're considering the derivative here that we found in part A in a previous video, and we are going to identify the function that's represented by the differentiated series. We're also going to do C in this video. So first thing that I'm going to do is factor out anything common that I can. Okay, so I can factor out a 42, obviously, out of every term. And the highest power of x I can factor out is an x to the 5th. So I'll factor that out, and let's see what I get. 1 minus x to the 12th plus x to the 24 minus x to the 36 plus dot, dot, dot. Okay. Now this might look familiar to you. This may look like the geometric series that we were doing earlier. If you say that u is equal to, let's say u is equal to x to the 12th. So we'll get 42x to the 5th, and that would give us 1 minus u plus u squared minus u cubed plus dot, 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 right? Okay, so that's looking even more like a geometric. If we had a geometric that was, let's see, 1 over 1 plus u, right? Which is 1 over 1 minus a negative u. That's what we're looking at there. So our r in this particular case is negative u, or if we wanted to go back up here and do it at this point, our r would be negative x squared. Okay, so either way we do that, we can now expand this out using a geometric series, okay, which would give us, let's see, 42x to the 5th. Let me move that up a little bit. And then we'd have 1 over 1 minus a negative u, which is 42x to the 5th times 1 over 1 minus a negative x squared, or x to the 12th, excuse me, which is 42x to the 5th. Let's go ahead and move that to the inside, and then 1 plus x to the 12th. Okay, so that is the function that's represented by this differentiated series. So that is d times 7 tangent inverse of x to the 6th dx. Okay, so that takes care of B. Now C says, what is the interval of convergence? Okay, well, since we've already recognized that this is actually a geometric series, then in order for a geometric series to converge, your r has to be less than 1. And our r in this particular case was, well, it was u, but that was actually negative x to the 12th. So if r is less, or absolute value of r is less than 1, then it converges, right? So if that's the case, then negative x to the 12th, let's put absolute values, not parentheses. Negative x to the 12th is less than 1. That also converges, okay? So given that, we know that that means negative 1 is less than x to the 12th is less than 1, and then take the 12th root, you still get negative 1 is less than x is less than 1. And that is where that thing is going to converge.